Hello everyone, welcome to Enviro Pioneers. In this video, we will learn the basics of coordinate reference system and the difference between geographic and projected coordinate system. When we use the term spatial data, it refers to the data which also include the coordinate values. And having the coordinate values, it provides a frame of reference for the data and it helps us to locate the features on the surface of the earth to align the data relative to the other data, to perform spatially accurate analysis, to add or to edit the data, or to create the maps. Suppose if you are working on a groundwater monitoring project and for the physico-chemical analysis, we have collected the water samples from different tube wells and we mark them on the map with the help of their coordinate values. And we want to justify the result of our physico-chemical analysis along with different data. It can be secondary data or it can be the remote sensing data. For example, here we have some of the thematic layers: geology, geomorphology, land use, lineament density, drainage density, soil, slope and the rainfall. So these are the factors which affect the groundwater in any particular area. So to integrate the information of all these thematic layers along with our sampling location points, we have to select an appropriate CRS so that all the data sets, satellite imagery or the secondary data, they are aligning well with our groundwater locations. So if you are working in this field, you must be familiar with this term CRS. But if you are new in this field, you will surely come across this CRS in the GIS. So this CRS, it stands for Coordinate Reference System, and it is a framework that defines how spatial data is mapped onto the Earth's surface. The coordinate reference system, it provides a way to represent the geographic features in either three-dimensional or two-dimensional space by using a set of rules, or we can say mathematical calculations, for defining how the geographic coordinate in terms of latitude and longitude or projected coordinates, which are x and y, it relate to the locations on the earth. Using the coordinate reference system in GIS, it ensures the spatial data from different sources, they align correctly on the map, and it helps in the accurate spatial analysis and the measurements essential for defining the spatial extent and the scale of a GIS project. This coordinate reference system is of two types: geographic coordinate system and the projected coordinate system. And this geographic coordinate system, it is also referred as GCS, and it is a reference framework which defines the location of features on a model of the earth, and the units are generally angular, usually degrees. So it generally defines where the data is located on the earth's surface, while the projected coordinate system, it is planar or flat. So it includes the GCS, but it converts the information of the GCS into a flat surface using the projection algorithm and other parameters. And the units of PCS are linear, most commonly in meter. So this PCS, it tells the data how to draw on a flat surface like on a paper map or on a computer screen. In this image, we can see that the geographic coordinate system, it tells us where on the earth the data should draw, while the projected coordinate system, it tells us how to draw the earth on a flat surface. So GCS, it is necessary for the data to know where exactly on the earth surface it is located, while the PCS, it is necessary to draw the data on a flat map. Till now, whatever we discussed in the map projection and the coordinate system, there we assumed the shape of the earth as a perfect sphere. But in reality, the earth is not a perfect sphere. It is in the form of a spheroid with the poles a bit closer towards the center in comparison to the equator, And this bulging of the equator is mainly because of the centrifugal force caused by the rotation of the earth, and also due to the different landform, that is high mountains and the deep ocean trenches, the surface of the earth, it is very uneven. So to address these two issues, we have the geographic coordinate system, which is used to define the locations on a model of the surface of the earth. In the geographic coordinate system, we mainly use the network of imaginary lines to define the location. But in order to draw these lines, we need a model of the earth that is at least a regular spheroid, if not a perfect sphere. And sometimes we incorrectly call this GCS as a datum, but a datum is only one part of a GCS. So geographic coordinate system, it includes the angular unit of measure, a prime meridian, and the datum, which is based on a spheroid. So to establish a georeferencing framework, an assumption is made to conceptualize the earth as a simple solid shape that can be represented mathematically. And for this, the ellipsoid geoid model is the most commonly used mathematical surface which represent the surface of the earth. This ellipsoid, it is the reference surface for the horizontal positions, while the geoid is for the elevations. So the spheroid shape and the uneven surface of the earth, it is considered in two models. One is the ellipsoid and second is the geoid. And then combination of the geoid and the ellipsoid, it forms a datum, which is the ellipsoid geoid model. Now firstly let us see what is the ellipsoid. As the earth, it is slightly flattened at the pole, we can now consider the earth as the rotating ellipse. So here, this is the shape of the ellipse where the equatorial plane, so the equatorial axis, this is referred as the major axis, and the radii, it is referred as the semi-major axis, while the polar axis is referred as the minor axis and the radii, it is referred as the semi-minor axis. So the semi-major axis is represented as A and the semi-minor axis is represented as B. And the physical shape of the real earth, it is closely approximated by the mathematical surface of the rotational ellipsoid. So if we rotate this ellipse on its minor axis, so we get the ellipsoid. So this rotational ellipsoid is the solid which is obtained by rotating the ellipse on its minor axis. And we also use the term spheroid. So it is the shape that is generated by rotating an ellipse around one of its axes. So the spheroid term is used for the rotational ellipsoid. And the ellipsoid is the reference system for the horizontal coordinates, and the difference in the length between the equatorial and the polar radii is 11.5 kilometer. So the polar axis is about 23 kilometers shorter than the equatorial axis. A spheroid is defined by either the semi-major axis and the semi-minor axis, or by the semi-major axis and the flattening. So this flattening, it is the difference in the length between the two axes, and it is expressed as the fraction or the decimal. And this flattening, it can be calculated by the following formula. So the F can be calculated by the difference between the semi-major and the semi-minor axis divided by the semi-major axis. And the value of the flattening, it ranges from 0 to 1. So if the value is 0, it means both the axes are equal, resulting in a complete sphere. The flattening of the earth, it is approximately 0.003353, and as this value is a very small value, so usually the quantity 1 by f is used instead. So when you will search on the internet about the flattening of the earth, you will get something like this. So when you divide this value 1 divided by 298.25, you will get exactly the same value. Earlier, the computation of equatorial and the polar radii were made by the measurements in a particular area of interest, and the ellipsoid which were created that fit to that part of the earth surface. As we can see in this image, the red one, it is representing the earth surface, while the black one, it is representing the ellipsoid or the spheroid created. So if the measurements were done from this particular part, so the ellipsoid which were created that fits this part of the earth well, while in the other part it fits very poorly. So in this case, the center of the ellipsoid, it is at different point in comparison to the center of the earth mass. So since 1960, with the help of the satellite based observation, we have the new values of the equatorial and the polar radii, and with the input from the organizations like the International Union of Geodesy and the Geophysics, with the more accurate measurement of the equatorial and the polar radii, new ellipsoids have been developed, and the ellipsoid which uses the center of mass of the earth as the origin, they are referred as the geocentric or the earth-centered ellipsoid. And an ellipsoid that offers a close approximation of our planet is known as the reference ellipsoid and is used as a reference surface for measuring the latitude and the longitude. Now, coming to the second issue related to the uneven surface of the earth. So due to varied topography, as the mountains they have more mass than the valley, so the pull of gravity it is stronger near the mountains, and because of these large and small variations in the size, shape and the mass distribution of the earth, it causes the slight variation in the gravitational pull, and this variation it determines the shape of the planet's liquid environment, that is the water. If we consider a scenario where we remove the tides and currents from the ocean, the water would settle onto a smoothly undulating shape, rising where the gravity is high and sinking where the gravity is low. So this irregular shape, it is referred as the geoid and a surface which defines the zero elevation. So using the complex mathematical calculation and the gravity readings on the land, the surveyors they extend this imaginary line throughout the continents, and this model it is used to measure the surface elevations with high degree of accuracy. So the geoid is a model of the global mean sea level that is used to measure the precise surface elevations. So this geoid, it means earth alike, and it is the shape of earth that would be formed if the oceans were allowed to flow freely under the continents to create a single undisrupted global sea level covering the entire planet earth and adjusted to the gravity. And this geoid, it is defined as the equipotential surface which is made using the precise measurement of the gravity across the continents and around the world. And because of the earth composition, the gravitational force it varies, and it is high over the continents because the crust is thicker, and this is low over the ocean floors, and this results in the irregular geoid. Thus, a geoid model is created which represent the mean sea level of the earth, and it is used as the reference surface for measuring the elevations. So here we can see that this is the surface of the earth, and then here we have this is the depression. At some places we are having the mountains. So this blue one it is representing the geoid, and the orange dotted line it is representing the ellipsoid. So the ellipsoid it is used for measuring the latitude and longitude, while the geoid it is used for measuring the altitude. Due to irregular shape of the geoid, there may be certain variations in the measurement made. For example, here in this image if we see, here both geoid and the spheroid they are at the same height. But here in this part where we are having the ocean, ellipsoid it is above the geoid, while in the case of the mountain, the geoid is above the ellipsoid. So there is difference in height of both the layers, and also if we calculate the vertical. For example, here if we see for the blue for the ellipsoid, this dotted line is the vertical, while for the geoid this straight line is the vertical. So this is referred as the deflection of the vertical, and it comes under the geoid undulation. And within this undulation height, which is also known as the geoid height or the geoid ellipsoid separation, this is the difference in elevation between the geoid and the ellipsoid. And this undulation height, it is very important in the geodetic and the surveying application because it provides the accurate height information for mapping and the navigation. Now coming to the datum, which is the combination of the geoid and the ellipsoid, and this is a model which describes the position, direction and the scale relationship of a reference surface for the positions on the surface of the earth. So the datum, it is the mathematical combination of both geoid and the ellipsoid, and for the survey and the mapping over the larger area, mainly geodetic datum is used. Geodetic datum, it takes into account the position of the origin for calculating the latitude and longitude. So this is the center of the Earth's mass. Then orientation of the geodetic network and the parameter of the reference ellipsoid and also the geoid undulation at the origin. So the datum is the combination of the geoid and the reference ellipsoid that best represent the Earth's surface. And if we make the ellipsoid by using the local measurement, that could fit a particular part of the earth very well, but there is possibility that it will not fit in another part. For example, here we can see that this is fitting here very poorly. But when we create the ellipsoid or the spheroid, taking the center of the earth mass as the origin, it best fit to the earth as a whole. So the datum which is created using the geoid and the geocentric ellipsoid, it is referred as the geodetic datum, and this datum, it provides a better fit to the geoid globally than the conventional datum. So here we can see that this blue one, it is representing the geoid, the red one is representing the global datum, and this one is representing the local datum. So the local datum is the one which is fitting best in a local area, but the global datum is the one which is made using the geocentric ellipsoid and it best fit globally. So here we can see the difference between the global datum and the local datum. So the local datum which is made for this particular area with the center of ellipsoid here, and this is the center of mass of earth. So the local datum will fit for a particular area very well, but it will fit poorly in the other part. But in the global datum, the center of ellipsoid that coincide with the center of mass of earth, and it provides a good fit overall. So the datum, it provides a frame of reference for measuring the location, and it defines the origin and orientation of the latitude and the longitude lines. And the global geodetic system, they are developed for georeferencing based on a single point at the center of the earth. The World Geodetic System of 1984, that is also referred as the WGS 84, it is geodetic datum, that is the standard ellipsoid model of the earth, and it is mainly utilized in our GPS system. The Geographic Coordinate System, this is appropriate for the global data sets and the applications like the satellite image repositories and the GPS satellites. Because these satellites are continuously revolving around the earth, they mainly use the datum WGS 84 because using global datum which is best fit for the earth, that will be suitable for obtaining the accurate information about the different locations on the earth. Using the geographic coordinate system, we get the latitude and the longitude values, which are traditionally measured either in the decimal degree or in degree, minute and second. Though these latitude and longitude can locate the exact position on the surface of the earth, but they are not uniform unit of measure because only on the equator, the distance represented by 1 degree of longitude is equal to the distance represented by 1 degree of latitude. But as we move above and below the equator, the length of the parallel, it gradually decreases, and also the meridians, they converge towards the pole, and the distance represented by 1 degree of longitude decreases to 0 at the pole. On the Clark 1866 spheroid, 1 degree of longitude at the equator, it equals 111.321 km, while at the 60-degree latitude, it is only 55.802 km. And because the degrees of the latitude and longitude, they don't have the standard length, we cannot measure the distance or the areas accurately, or we cannot display the data easily on the flat map or on a computer screen. So for this, we need the projected coordinate system. So the projected coordinate system, these are the planar system that use the linear measurement for the coordinate rather than the angular unit. So here we mainly use different map projection, which are the algorithm which defines how to present the round earth on a flat map. But the projection which we use here, that is only one parameter in the projected coordinate system. In addition to the projection, a projected coordinate system, it also includes a geographic coordinate system because this is necessary to define the earth model, then a unit which is often in meters, and a set of parameter values like the false easting, central meridian, standard parallel, and so on, which vary depending upon the projection. And these can be used to center the projected coordinate system on different parts of the world. There are many different type of projections depending upon which particular property they are preserving. For example, here we have the Albers equal area conic projection, equidistant conic projection, Lambert's, and the conformal. So the conformal, it generally preserves the shape of the features. Equidistant, here the distance between two features that is preserved, and the equal area conic projection. So mainly here the area of the feature, it is preserved. There are many different map projections. Here we have some of the representation, and each of the map projection, they display the earth in a different way. Some are good for preserving the areas on the map, others are at preserving the angles, distance, or the shape. So depending upon what is the objective of your study, accordingly you can select different projection within the geographic coordinate system. Thus, the projected coordinate system is used to transfer the information of the real-world features on a computer screen or on a flat paper. One of the most commonly and widely used projection in projected coordinate system is the UTM projection. So, we will cover this particular topic in detail in our next video. These are the references for today's topic. The first one is a book, that is the concept and the technique of the geographic information system, and rest are the website from where the content and the images have been taken. Thank you for your continuous support. We will meet soon in the next video covering the basics of the UTM projection. Thank you.